Tonight, we're going to explore a calculation that turns one of our oldest hopes inside out. Every year, we get better at building things that move. In 1804, the fastest machine on Earth was a steam locomotive that moved at walking pace. 200 years later, a spacecraft left the solar system at 38,000 miles an hour. Across those 2 centuries, the top speed of human machines doubled roughly every 15 years. Which means the ships we build 100 years from now will be far faster than anything we could build today. So the plan has always been simple. Keep improving, then go. But when you run that plan through the arithmetic, it doesn't say go, it says wait. The best departure date is somewhere around 900 years from now. Everything we send before then arrives second. And by the end of tonight, you're going to understand why the silence we hear when we point our instruments at the sky might not be an absence of anyone out there. It might be everyone out there, running the same calculation and reaching the same answer. If you find questions like this one worth sitting with, please subscribe and leave a like. It's a small thing, and it helps this channel reach the people who'd actually want to hear it. And tell us in the comments where you're listening from tonight and what the clock says where you are. This is a video about waiting, and I like knowing that some of you are hearing this sentence at 4 in the morning and some of you over breakfast, all at the same moment. Now, let's begin. Let's start with what we know. There's a spacecraft out there right now called Voyager 1. It lifted off from Cape Canaveral on September 5th, 1977. It has been flying ever since. 49 years, no stops, no refueling, no repairs, no second chances. It is the farthest thing our species has ever made, and it is still talking to us. On November 18th, 2026, Voyager 1 crosses a line that nothing built by human hands has ever crossed. At that moment, it will be exactly 1 light day from Earth. 16,094,000,000 miles. Sit with that for a second. 1 light day. That's the distance light covers between one sunrise and the next. Light does it in 24 hours. Voyager needed 49 years. And Voyager isn't slow. Nothing we've ever built is faster at getting away from the sun. It's moving at about 17 kilometers every second, which is roughly 38,000 miles an hour. If you could put a car on that trajectory, at highway speed, it would need something like 29,000 years to cover the same ground. Now, hold that number in your hand and look at the nearest star system to our own, Alpha Centauri, 4¼ light years away, which means in the units we just built, about 1,550 light days. Voyager took 49 years to cross one of them. We don't have to do the multiplication out loud. You already know what it gives you. Tens of thousands of years. Longer than agriculture, longer than writing, longer than any structure, any language, any nation that has ever existed on this planet, by a factor of 10. And this is the point where almost everyone reaches the same conclusion. And the conclusion feels obvious, and it feels complete. The problem with reaching another star is distance. Space is too big, and we are too slow. Fix the speed, and you fix the problem. Build a better engine, and the stars open up. That's the story we've been telling ourselves since we started telling stories about this at all. Here's the thing. Distance is the easy part. Distance is a number. It doesn't argue. It doesn't change its mind. It doesn't hold committee meetings or run out of funding. We can attack a number with engineering. And engineering is the one thing our species is unambiguously good at. Give us 4 centuries and a clear target, and we will find a way to move something faster. We've done it over and over. The thing that stops us isn't out there in the dark. It's a piece of arithmetic, and it fits on a single sheet of paper. And once you've seen it, you can't unsee it. But before we get to the arithmetic, let's stay with Voyager for a moment. There's something in its daily operation that makes the scale physical rather than abstract. Right now, when engineers want to send Voyager 1 an instruction, the signal takes about 23 hours to arrive. 23 hours at the speed of light, moving as fast as anything in this universe can move. Then the spacecraft does the thing. Then its answer takes another 23 hours to come home. Imagine that. You ask a question on Monday morning. You find out on Wednesday morning whether it was even heard.
You can't troubleshoot like that. You can't react. If something goes wrong out there, it has already been wrong for a day before you learn about it. Your fix arrives a day after you send it. The people running that mission are working blind across a gap that no amount of urgency can close. And Voyager is close. Voyager is our backyard. Voyager hasn't gone anywhere yet. That's the shape of the problem as most people understand it. Enormous distances, crushing delays, machines that outlive the careers of the people who built them. Hard, but the kind of hard that yields to persistence. The real problem showed up 16 days after Voyager 2 left the ground. Voyager 2 launches on August 20th, 1977. Voyager 1 launches on September 5th. 16 days later. They're twins. Same design, same instruments, same golden record bolted to the side. They come off the same production line and go up on nearly identical rockets. The only meaningful difference is the path. Voyager 1 gets the faster route. It's aimed on a shorter arc through the asteroid belt and a tighter swing past Jupiter. And on December 15th of that same year, less than 4 months after leaving Earth, Voyager 1 catches its older sibling and goes past it. It never gives the lead back, not once, not in 49 years. Think about what that means for the people who worked on Voyager 2. They watched their spacecraft leave first. They watched it clear the atmosphere first, cross into deep space first, do everything first. And within a single season, it was in second place permanently, passed by a machine that was still sitting on the pad while theirs was already flying. The first version of the story is small. 16 days, a few months, one solar system. Now watch it happen again at a scale that actually hurts. Pioneer 10 launches in March of 1972, 5.5 years before the Voyagers. It's the first spacecraft to cross the asteroid belt, the first to fly past Jupiter, the first thing we ever built that was on a path to leave the solar system entirely. For a quarter of a century, Pioneer 10 is the farthest object humanity has ever placed anywhere. It holds that title for 26 years. On February 17, 1998, at about 5:10 in the evening Eastern Time, Voyager 1 passes it. The crossing happens 6.5 billion miles out, far enough that sunlight arrives there 10 hours old. The two spacecraft aren't near each other, incidentally. They're heading in nearly opposite directions. A race with no track and no finish line, scored purely by how far each one has gotten from home. The project's scientist at the time described it as a baton being passed. That's a generous way to put it. What actually happened is that a machine launched 5.5 years later overtook a machine with a 26-year head start. It took the record permanently. Pioneer 10 will never be in front again. Why? Because Voyager 1 flew past Saturn on a very particular trajectory and stole a piece of that planet's orbital energy. It didn't carry the speed with it from Earth, it picked the speed up along the way. And one detail should stay with you. Pioneer 10 was not badly built. Pioneer 10 was excellent. It did everything asked of it and more. Its only failure was chronological. It left too early to use the trick that hadn't been worked out yet. One more, and this one runs the other direction, which makes it worse. New Horizons launches in January 2006 on its way to Pluto. It leaves Earth faster than any spacecraft in history, 16.3 kilometers per second at departure, straight onto an escape trajectory with nothing held in reserve. It passes the orbit of the Moon in 9 hours. Apollo took 3 days, the fastest departure ever recorded.
And New Horizons will never catch Voyager 1. Not ever. It's falling behind a little more every year, and it will keep falling behind for as long as both machines exist. Because Voyager got Jupiter and Saturn, New Horizons only got a rocket. So the fastest launch loses to the better route. The earliest launch loses to the later launch. The 26-year lead evaporates in an afternoon. This is shocking discovery number 1, and it's not a theory. Being first out of the gate has almost nothing to do with being first to arrive. We have measured this twice, with real hardware inside our own solar system, in the space of a single human lifetime. Every one of those overtakings happened over months and billions of miles. Now ask what happens over centuries and trillions. January 1944. A science fiction magazine runs a short story called Far Centaurus. The world is in the middle of a war. The story is about something else entirely.
4 men have a drug that holds the human body in something like hibernation. It works, mostly. It has about a 10% chance of killing you each time you go under, which the story mentions almost in passing. They build a ship and set out for Alpha Centauri. The flight is going to take 500 years, which is about as long as printed books have existed. The men take turns waking up, years apart, then decades apart. One of them wakes early in the voyage and finds one of the others already dead in his bunk. He suits up, disposes of the body, writes it in the log, and goes back to sleep. Another wakes and sees something burning behind them in the dark. Another leaves a note about whether the third man is losing his mind. 5 centuries of that. Then they arrive, and Alpha Centauri is full of people. Human people, cities, industry, a civilization several hundred years old. All of it built by people who left Earth long after these 4 did, on ships that got there in a fraction of the time. The 4 travelers aren't heroes. They're not even news. They're relics who smell wrong, who can't speak the language, who can't follow the physics, and who have nothing anybody needs. That's 1944, before the transistor, before the first orbital rocket, before anyone had put anything at all into space. And it wasn't even the author's idea. The concept came from his editor in a letter, laid out almost in full. Send a sleeper ship and have it arrive to find the destination already settled. The author changed some details and wrote it up. The bones were handed to him, which tells you something. This problem was visible from the ground floor. Nobody needed to know anything about propulsion to see it. We only needed to notice that machines keep getting better, and that a long voyage is long enough for them to get better while you're inside one. It took another half-century for anyone to give it a name. And then 3 names arrived at once from 3 different directions. One phrase came out of a workshop in 1994 on whether we were ready to send robotic probes between the stars. Zeno's paradox in reverse. In the old paradox, the runner never reaches the finish line because there's always another half to cross. Here, it's the opposite. The finish line keeps coming toward you, and it keeps arriving without you. Around 1999, someone working on advanced propulsion coined a colder version. The incessant obsolescence postulate. No matter when you launch, a later probe will get there sooner and with better instruments. And in 2006, a third name, and this is the one that stuck. The incentive trap. 3 names, 1 dread, and for 62 years, that's all it was. A feeling in the stomach of anyone who thought seriously about leaving. Then somebody sat down and put a number on it. 2006. A paper appears in the Journal of the British Interplanetary Society, written from Seville in Spain.
It isn't long. It doesn't require anything past high school mathematics, and it starts by setting a scene rather than an equation, which is unusual for a technical paper and probably deliberate. Picture this, the paper says. Technological growth has finally given us an interstellar ship. It's built. It works. The destination is Barnard's Star, about 6 light-years out, which, at the time, was the most interesting nearby target anyone knew of. The crew is assembled and they've accepted the terms. They will never see Earth again. They will never see anyone they left behind. They're going to spend their lives and their children's lives in a metal shell moving through nothing. And this, the paper says, is the moment to pause and consider the following. Civilization is growing faster every day. Science will produce faster ways to travel.
It might even solve the problem of moving at the speed of light, or past it. If that happens while this ship is still in transit, people who leave later will arrive first. Everything these people gave up will have been given up for nothing. That's the trap, stated plainly. Now watch the author turn it into arithmetic. Start with the speed you can actually manage today. Call it 1/2000th of the speed of light. At that rate, 6 light-years takes about 12,000 years. 12,000 years. Let me put that somewhere you can stand. 12,000 years ago, the last ice age was ending. There were no cities, there was no farming worth the name. The ancestors of everyone you have ever met were hunting and gathering across a landscape that hadn't finished melting. If a ship had left then, at that speed, it would be arriving at Barnard's Star roughly now. Now add growth. Assume that the speed we can achieve doubles every 100 years, which over the long run is a conservative guess. How long do you have to wait before you can make that same 6 light-year trip in 100 years instead of 12,000? About 690 years. So do the sum. 690 years of doing nothing plus 100 years of flight is 790 years from now, against 12,000 years if you launch tonight. Waiting 7 centuries gets you there 11,000 years sooner. Now go back into that room. You have the ship. It's finished. It's fueled. The crew is standing in front of you and they've said yes. And some of them have children, and the children have been told. And the piece of paper on the table says something simple. The most useful thing you can do for this mission, for the goal, for the actual arrival at the actual star, is to cancel it. Not delay it, not scale it back. Cancel it, and tell your descendants 25 generations from now to try again. That's an ugly conversation, but it's a conversation with an answer, and the answer is a date. And a date is something a civilization can plan around. Wait until the year 2800, more or less, and then go. Except that isn't what the arithmetic says either. Because if you can see that waiting 690 years is smart, so can everybody else, including everybody who exists 690 years from now. They'll be looking at the same curve you are. They'll be asking whether they should wait a little longer still. And when we follow that question all the way down, the curve does something nobody expected. We draw it like this, and it's worth going slowly because everything else tonight rests on this one shape. On the bottom of the page, put waiting time, 0 years on the left, growing to the right. On the side of the page, put the total time from right now until somebody actually stands on the destination. That total is 2 things added together. How long you sat on Earth, plus how long the flight took once you left. Now plot it. On the far left, where you leave immediately, the total is enormous. 12,000 years, all of it flight. As you move right, the line drops fast. Every century of waiting buys a speed increase that cuts the voyage by a huge chunk. Wait 100 years, save thousands. Wait 200, save thousands more. The line keeps falling. It falls steeply, then less steeply, then it flattens out. And then it turns and starts climbing again. Because eventually, the voyage can't get much shorter. You've already cut it from 12,000 years to a few centuries, and then to a century. The savings from waiting another 100 years keep shrinking. The waiting itself still costs a full 100. At some point, the two effects cross over. After that, every extra year you wait is an extra year added to your arrival date, no matter how fast your ship gets. There's a bottom to the curve, a single lowest point. Find it for a doubling time of 100 years, and it sits at about 637 years of waiting. Total time from today, roughly 782 years. Now look closely at what that departure involves, because this is where it stops being intuitive. The ship that leaves at the bottom of the curve does not make the 100-year crossing. It makes a 145-year crossing. It's slower than the ship you were imagining. It's a longer, harder, more expensive voyage than the one you would have chosen if somebody had asked you to pick. And it wins. The faster ship needed another 53 years of development before it could exist. 53 years of sitting still costs more than 45 years of extra flying. The best departure is not the best ship. It's like leaving after your neighbor and still arriving first, because he took the old road and you waited for the new one. Let me say what that means on both sides of the bottom. The two halves behave completely differently, and the difference is the whole story. Before the bottom, you are in the trap. Anyone who leaves in this stretch will be overtaken. Not might be, will be. Somebody leaving later with better hardware will pass them in transit and be waiting at the destination when they arrive. Every departure in this region is a departure into second place. After the bottom, the trap is gone, and it's replaced by something else. Now the later ships are faster and they still lose. They can't make up the waiting time. Somebody who left at the bottom of the curve is already there and has been for years. Nothing anybody builds afterward closes that gap. Later ships are faster and they still lose. This is shocking discovery number 2. There is exactly one moment for any given destination and any given rate of progress when leaving is correct. Before it, you're wasting the voyage. After it, you're wasting the wait. And the moment itself is a knife edge. It has to be found by a civilization that cannot test it, cannot rehearse it, and gets one shot. We ran that with an optimistic starting speed, something faster than anything we have ever actually flown. Use a real one and it gets worse. So let's do that. Take the speed of an actual spacecraft, the kind we know how to launch, the kind that has flown. Something in the class of a probe leaving Earth on a direct escape trajectory. That's roughly a 20,000th of light speed, an order of magnitude slower than the figure we just used. And instead of assuming a 100-year doubling, use something anchored in the physical world. The power you can put behind a ship scales with the energy your civilization produces. World energy consumption grew at about 1.4% a year through the 1990s and into the 2000s. So take 1.4% as the long-run rate at which our capacity to move things improves. Now find the bottom of the curve. 966 years of waiting. Then a voyage of 145 years. Total time from tonight to arrival, about 1111 years. 966 years. Turn that around and walk backwards instead of forwards, because forwards is abstract and backwards is not. 966 years before tonight is the year 1060. The Norman conquest of England hasn't happened. It's 6 years away. There is no university anywhere in Europe, not one. Oxford won't start teaching for decades yet. The Aztec Empire doesn't exist. The Inca Empire doesn't exist. Neither does gunpowder in European hands, or the mechanical clock, or the printing press, or the concept of zero in most of the Western world. The English you're listening to right now did not exist. Not as an accent, not as a dialect, as a language. If you were handed a page written in 1060 by someone in London, you would not recognize it as related to anything you speak. That is the distance from here to the launch date. And now the question that the arithmetic doesn't answer, and can't. Who holds the plan? Seriously, who? Which organization signs a contract in 2026 that comes due in the year 3000? Who audits it in the year 2400 to confirm the numbers still hold? Who pays for the storage of the design documents through 966 winters? What happens the first time a government decides the money is needed elsewhere? It will happen. Then happen again, roughly 40 times before the launch window opens. Who tells the crew's great-great-grandparents' great-great-grandparents that their descendants are still going? There's no answer in the paper, because it isn't that kind of paper. It's arithmetic. Arithmetic doesn't do institutions. But we can feel the shape of the problem now. The equation hands you a date. Holding a date is a different discipline entirely, and we have never once demonstrated that we can do it. At this point, the obvious response is the one you're probably already forming. Fine, so make progress faster, push harder, invest more, accelerate the curve, and the launch date comes toward us. It's the right instinct. It's also exactly backwards. Run the numbers at 5% annual growth instead of 1.4. That's a serious acceleration, far above anything sustained in the real world for long. And yes, the waiting time collapses. The bottom of the curve moves to about 327 years from now. 3 centuries instead of 10. That sounds like a win. And in one narrow sense, it is. But look at what happened to the shape of the curve while you weren't watching. It didn't just move, it got sharper. At slow growth rates, the bottom is broad and forgiving. You can leave 50 years early or 50 years late, and the difference in arrival time is a handful of years. The curve is nearly flat down there. Mistakes are cheap. At high growth rates, the bottom is a spike. Leave 20 years off the mark, and the penalty isn't a few years, it's decades of extra flight or decades of missed opportunity. The faster your civilization improves, the more precisely it has to time a decision it can only make once. Using a growth rate it can only estimate, aimed at a target it has never visited. Faster progress doesn't loosen the trap, it tightens the jaws. And now run it the other way. Suppose growth slows, suppose we hit resource limits, or the energy curve bends, or the century turns out to be harder than the last one. Take 0.5% a year. The bottom of the curve moves out to about 2,287 years from now. The voyage from that departure lasts 400 years. Sit with the 400-year part, not the 2,000, the 400. A 400-year flight is a ship where nobody who walks up the ramp is related to anybody who walks down it. Not a grandchild, not a great-grandchild. Somewhere between 12 and 16 generations. All of them born inside, all of them dying inside, all of them maintaining machinery designed by strangers for strangers. The people who boarded made a promise to people they could not imagine. And the people who land inherit a mission they never agreed to. So slow growth gives you an unbearable voyage. Fast growth gives you an unhittable window. There is no setting of the dial that makes this comfortable. And then there's the argument that's supposed to rescue everything, which is the one about acceleration itself. Some people believe technological progress isn't just exponential, but compounding, curving up towards some point where the rate of change becomes effectively vertical. Machine intelligence designing better machine intelligence. Discovery feeding discovery. If that's coming, surely it dissolves the whole problem. The author of the weight calculation went back and looked at that specifically in a follow-up paper. His conclusion is the least comfortable sentence in the entire literature. If growth accelerates without limit, the incentive to leave doesn't improve, it collapses. Think it through. The stronger your belief that next century's ships will beat this century's, the more certain you are that anything you launch now is a wasted sacrifice. A world that genuinely expects a technological explosion is a world where no one will fund a Starship. Every investor can see where the return goes, to whoever launches after the explosion. The expectation of a miracle is itself a reason to stay home. This is shocking discovery number 3, and it's the one that reverses the story we started with. We assumed progress was the thing that would eventually carry us out. It isn't. Progress is the mechanism of the trap. Every improvement we make is another argument for not going yet, delivered by the very people trying hardest to get us there. The better we get, the more sense it makes to stay. That's not a failure of nerve, it's the answer the equation gives. And here is the part nobody planned for. All of this rests on one assumption, stated at the very top and never questioned afterward: that the speed available to us keeps growing. Every version of the calculation, at every growth rate, in every paper, takes that as given. 200 years of history said it was safe. Voyager 1 left the Sun's grip in 1977 at about 17 kilometers a second. 49 years later, that is still the record. Not New Horizons, which departed Earth faster than any object ever built and is still losing ground. Not anything else. Nothing we have launched in half a century leaves the solar system faster than that machine. It was designed with computers weaker than the one in a modern washing machine. It was assembled by people who are now mostly retired or dead. The curve that this entire argument depends on has been flat in the one number that actually matters for the whole of living memory. There's a standard answer to that, and it arrives fast. It usually arrives before the objection has finished. Someone will invent something. That's the answer. We haven't beaten the record in half a century because we haven't had the breakthrough yet. When it comes, the whole curve gets rewritten, and none of this arithmetic matters. It's a comforting answer. The paper takes it seriously, and then it goes and looks at what breakthroughs have done. The history is not kind. Take quantum theory. The idea of the energy quantum shows up in 1900. Einstein uses it in 1905. By 1926, the theory exists, built by the best minds of the century working flat out. And nearly 50 years pass from that first quantum before anything usable comes out of it. The mathematics kept producing infinities. Nobody could extract a real physical number from it until somebody worked out the tricks in the late 40s. 50 years. That's an entire working life, start to finish, between the idea and the ability to calculate with it. Entanglement is worse. It's described in 1935 as an objection rather than a discovery. Somebody points at it and says, "This can't be right." Roughly 70 years pass before it turns into anything you can build with. 70 years is longer than most marriages last. Longer than most countries keep the same constitution. And then there's fusion, which is the one that should really bother you. Physicists worked the principle out in the 1930s. We knew what makes the stars burn. A fusion bomb went off in 1952, which proves the reaction works at scale. People have been trying to make it produce useful power for over 70 years at enormous expense in every industrialized country on Earth. There is still no fusion power station anywhere. There's no firm date for one either. We understood the physics before your grandparents were born. We still can't plug anything into it.
But the sharpest example isn't in physics at all. It's parked in a garage. In 1899, a Belgian engineer drove an electric car past 100 kilometers an hour. That's faster than the speed limit on most roads you'll drive on this week. It happened in a vehicle with no gasoline in it, before the Wright brothers flew. By 1900, more electric vehicles were registered in the United States than steam or gasoline cars. The electric car was ahead. It was winning. Then it lost, and it lost for a century. Not because of one decision or one invention, because the internal combustion engine received 100 years of small, grinding, unglamorous improvements, and the battery didn't. That mechanism is the part that matters tonight. Breakthroughs don't jump the curve, they get swallowed by it. A discovery lands, and for a moment it looks like a vertical line. Then comes the long part. Decades of engineering, materials work, failed prototypes, cost reduction, and slow adoption. By the time anything reaches a launch pad, the whole episode has been averaged back into the same gentle slope it always was. Which means the wait is not timidity. It isn't a failure of ambition, it's arithmetic. And the arithmetic has now survived every objection we've thrown at it. So the question stops being when we should leave. The question becomes what exactly we are waiting to reach. Now let's talk about the destination, because for 50 years we had one, and we were remarkably specific about it. Between 1973 and 1978, a group of engineers in Britain did something nobody had done properly before. They designed an actual Starship, not a sketch, a full engineering study, with mass budgets and failure modes running to hundreds of pages. They called it Daedalus. And the numbers are worth taking slowly, because they tell you what a serious attempt actually costs. At launch, Daedalus weighs 54,000 tons. That's about the weight of the Titanic. Of that, 50,000 tons is fuel. The scientific payload is 500 tons. So picture the Titanic. Now understand that 92% of it is propellant, and the part doing the actual work is about 1% of the ship. The engine burns by detonating pellets of fusion fuel and channeling the plasma out the back with a magnetic field. It does this 250 times a second. Your heart beats about once a second. In one of those beats, this engine goes off 250 times. It has to keep that up without a miss for 4 years. 2 stages, 2 years on the first, another year and 10 months on the second. At the end of it, Daedalus is moving at 12% of light speed. 12% of light speed crosses the Atlantic in about 1/5 of a second. Then it coasts at that speed in silence for 46 years. The fuel is helium-3, and helium-3 is almost non-existent on Earth. The plan was to mine it from Jupiter's atmosphere using robotic factories held aloft by hot air balloons in the clouds of another planet. That operation takes 20 years on its own. You'd spend your entire career mining the fuel and retire before the ship is fueled. And now the cruel part. Daedalus cannot stop. Carrying enough fuel to slow down at the far end would have made the ship absurd, so it doesn't slow down. After 50 years of flight, it crosses the target system at 12% of light speed, and the encounter lasts a matter of days. The design compensates as best it can. 18 smaller probes get fired ahead, released between about 7 years and 2 years before arrival. They spread out to catch whatever they can as the formation tears through. 50 years of flight, days of looking. Then it keeps going forever, into the dark, with everything it learned already sent home. Now, the question anyone would want answered before signing off on any of that. Why Barnard's Star? Because since 1963, an astronomer had been reporting planets there. Big ones, Jupiter class, detected by measuring tiny wobbles in the star's position on photographic plates. He'd been at it for decades. 10 people at a time averaged the measurements to cancel out individual bias. For about 10 years, a large part of the astronomical community accepted it.
It was the best evidence anyone had that planets existed anywhere outside our own system. That's why the engineers chose it. They weren't going to look at a star. They were going to look at worlds. Then another researcher took the same telescope and pointed it at a completely different star. He found the same wobble. Either two unrelated stars happened to have identical planets in identical orbits, or the wobble was in the instrument. It was in the instrument. The signal tracked maintenance work on the telescope's main lens, which had been cleaned and remounted 25 years into the observing run. The planets were never there, and it took another half-century to find out what actually is. In 2024, a planet at Barnard's star was announced. This time by measuring the star's motion toward us and away from us in the light itself. In March 2025, a second instrument on a different continent confirmed it, and 3 more besides. 4 planets, real ones at last, at the star we'd been aiming at since before the moon landing. The numbers are strange. Each planet has a minimum mass somewhere between 19 and 34% of Earth's. The heaviest of the 4 is made of about 1/3 as much material as the world under your feet. Their orbits are tighter than anything in our solar system by a wide margin. The years last 2.3 days, 3.2 days, 4.1 days, and 6.7 days. A year that lasts less than a week. You'd have a birthday every Tuesday. That's how close they sit to the star, and Barnard's star is a red dwarf, small and cool, about 1/6 the mass of the Sun. Ancient, too, somewhere between 7 and 12 billion years old, which makes it older than the Sun by roughly double. So where's the habitable zone? For a star that faint, it's the band where the year lasts between 10 and 42 days. None of the 4 planets are in it, not one. And the same measurements do something else, which is the part that closes the door. They're precise enough to rule out any planet heavier than 57% of Earth's mass anywhere in that zone. Something smaller could still hide there. Something you could stand on comfortably could not. This is shocking discovery number 4. The destination that the entire weight calculation was computed for has nowhere to stand. Not a disappointing surface, not a hard climate, nowhere. We designed a 54,000-ton ship for planets that didn't exist. We waited 60 years to find the ones that do. And they're 4 scorched rocks orbiting an old red star, each one whipping around it faster than you get through a work week. The target moved. And then, in 2017, the model moved too. A researcher in Germany went back to the weight calculation and did something nobody had done. He stopped guessing at the growth rate and went to look it up. He pulled 211 years of speed records. Real machines with real dates. 1804, a steam locomotive making about walking pace. 1894, the first production car topping out at the speed of a fast cyclist. 1903, a steam race car at 204 kilometers an hour, which is about the speed of traffic on an interstate. The same year, the first aircraft flew slower than that car by a factor of 18. By the 1940s, rocket planes were doing the cruising speed of the airliner you last flew on. And in 2015, Voyager 1 leaving the solar system. From walking pace to Voyager is a factor of about 17,000 in 211 years. Work that back into an annual rate and you get 4.72%. A doubling every 15 years. 4.72% is a savings account with a genuinely good interest rate. Nothing dramatic. Nothing that would make the news in any single year.
Just steady compounding decade after decade for 2 centuries. But it's more than 3 times the rate the original calculation assumed. And when you feed a higher rate into that curve, everything about the answer changes. Then comes the new result, and this is the one that offers a way out. So let's go slowly. There's a threshold. Call it the point where waiting stops being worth it. If the trip you're contemplating already takes less than about 22 years, waiting never helps. Not a little, not at all. The minimum in the curve doesn't move closer, it stops existing. 22 years is about the gap between a person being born and starting their first serious job. The reason is simple once you see it. Waiting a year costs you a full year guaranteed. But if the flight only takes 20 years, a year of improvement can only ever shave a fraction off it. The savings can't outrun the cost.
So the entire trap depends on the journey being long. Make it short enough and the trap simply isn't there. For Alpha Centauri specifically, the crossover speed works out at 19.6% of the speed of light. Reach that and there's no longer any reason to sit still. Go. And at the moment that paper was written, one project had been promising exactly 20%. Everything about that answer depended on the project actually getting built. April 2016. A press conference, a physicist in a wheelchair on stage, a billionaire beside him, and $100 million on the table. The concept was radical in the right way. Stop trying to build a ship, build a chip. A spacecraft weighing about a gram, roughly a paperclip. It's attached to a reflective sail 4 meters across, something like a small trampoline made of a material thinner than plastic wrap. You don't put an engine on it, you put the engine on the ground. An array of lasers fires 100 gigawatts at the sail for about 10 minutes. 100 gigawatts is what 100 million electric kettles would draw if you switched them all on together. Delivered in a single pulse at a target already thousands of miles up. 10 minutes of that and the sail is doing 20% of light speed. It passes Mars before lunch. It reaches Alpha Centauri in about 20 years, takes photographs and beams them home over the following 4. Real work happened. They found a candidate sail material and it can be made extremely thin. A laboratory built a miniature sail tethered at its corners and measured the push of a laser beam on it directly. They turned machine learning loose on the sail's geometry. It came back with a lattice of oddly shaped holes that accelerates faster than anything drawn by hand. That's real progress. Now the other column. Of the $100 million pledged, roughly $4.5 million went out the door, across about 30 contracts. 4.5 cents of every dollar promised. And since around 2024, the program has been on hold. We should be careful here because the story is contested and both versions are on the record. Press coverage in 2025 described it as a quiet demise, a project that ended without an announcement. People who worked on it argue the opposite. They say the first phase had a defined goal. It was to find out whether any of this was physically impossible, and that goal was met. Nothing show-stopping was found. The pause, they say, is a restructuring while broader support is sought. Both accounts can be true at once. A phase can succeed and a program can still stop. What neither account produces is a launch date. This is shocking discovery number 5. The one door out of the trap was a single project, funded by a single person, and it stopped. Which puts us right back at the number. 966 years, give or take, depending on which growth rate you believe. So now ask what that number costs the people who'd actually be on board. If this stretch of the journey has been as unsettling for you as it's been for me, please take a moment to like the video and subscribe. It helps more than you'd think. Because there's a version of this where we stop asking how fast the ship goes and start asking who's inside it. In 2018, 2 researchers ran that question through a simulation. Not a thought experiment, a model that tracks every individual on board across the whole voyage, including births, deaths, infertility, accidents, and who's allowed to have children with whom. They ran it thousands of times. The mission is a flight to the nearest known rocky world at a speed we can conceivably build.
That works out to 6,300 years. 6,300 years is about 250 generations. If your family had boarded when the pyramids were new, you'd still have thousands of years to go. The question was the minimum crew. How few people can you send and still land a genetically healthy population? The answer is 98. Fewer than that, and the numbers turn on you. With 25 breeding pairs and a strict ban on any inbreeding at all, the mission goes extinct in about half of all runs. Half. Not the mission fails to achieve its goals, the people die out, somewhere in the dark, with the ship still flying. A separate estimate takes a different approach. It asks what a minimum colony ship weighs. 500 people at 50 tons of structure and supplies each. 25,000 tons of dry mass. That's roughly 17,000 family cars, and not a gram of it is fuel yet.
Now the physical side, because speed itself does something to a ship that nobody expected until fairly recently. Interstellar space is close to empty. There's roughly 1 atom in a space the size of a sugar cube, and dust grains far rarer than that. At normal speeds, it's irrelevant. At 1/5 of light speed, it isn't irrelevant at all. A dust grain hitting the hull doesn't scratch it. The impact energy is high enough to explosively boil the surface material away, leaving a crater. Do that continuously, all the way to Alpha Centauri, and you lose about 0.5 millimeter of surface. That's the thickness of your fingernail, gone. The gas does something different and more insidious. Individual heavy atoms punch straight in, leaving tracks about 1/10 of a millimeter deep. A human hair is roughly 1/10 of a millimeter thick, so the front of your spacecraft ends up riddled to a depth of 1 hair, everywhere, for the whole crossing. Space is nearly empty. Nearly empty is enough. And none of that is the hard part. The hard part is the 98. Who chooses them? Who decides which families go and which don't? What do you tell the second generation, the ones born in a corridor who never chose any of it? What happens when a child in the 3rd generation says, "No, this isn't my mission, I want a different life"? Where does she go? What do you do with a person who is genetically necessary to a plan she never agreed to? Nobody has an answer. There's no version of this where somebody has an answer. And all of that assumes the voyage goes well. Let's consider the other end of it. In 2013, the man who first wrote down the weight calculation went back and worked out what happens on arrival. The outcomes are worse than being late. Start with the one that sounds like success. You arrive. Nothing overtook you. There's nobody there. The system is empty and untouched and yours. That's the bad outcome. Because if nobody passed you in centuries of flight, it means the civilization that launched you stopped launching. Something went wrong back home. The follow-up ships, the improved technology, the reinforcements you were counting on, none of it exists. You are alone with whatever you brought, permanently, with no way to ask for anything and no way to be told what happened. Now the other case. You arrive and there's a colony waiting, founded generations ago by people who left long after you did. You'd expect a welcome. There won't be one. The ships that passed you didn't stop, and the colony that greets you keeps its distance. And the plain reason is quarantine. Your immune systems and theirs have been separated for centuries.
If your crew spent the voyage in hibernation, their defenses have been suppressed the entire time. Nobody knows what's been sitting dormant in either population. Nobody is going to find out by shaking hands.
So you sit in isolation at the end of the longest journey ever made, being studied. And when the medical question is finally settled, the second problem starts, and it doesn't go away. You're obsolete. You have no training in the culture that got there first. You may not speak the language it turned into. The science your ship was built on is history to them, the way we regard steam engines. You have nothing to contribute technically and nothing to offer economically. Your worldview came from an epoch that ended before the colony was founded. You aren't colleagues, you're a burden, and possibly a political nuisance. Now, could the faster ships pick you up on the way past? Could they slow down and take you aboard? Run the numbers on that. A ship traveling at a 15th of light speed catches a ship traveling at a 20th. The closing speed between them is about 5 million meters per second.
At that rate, the gap between the Earth and the Moon closes in under 80 seconds. Your drive to work takes longer. Matching velocities isn't a rescue operation. It's a fuel budget nobody can afford, on top of a fuel budget nobody could afford in the first place. The later ship spent everything getting fast. Slowing down to your speed means throwing that away and then having to get fast again. And then there's the line at the end of the analysis, and it's stated flatly, without drama. There is no law operating in interstellar space, which means that deliberately launching after the minimum isn't a crime. Timing your arrival to land on somebody else's finished colony with better technology and a fresher crew. There's no court, it's a strategy. The earlier ship carries the risk, does the terraforming, builds the first shelter, loses the first generation. The later ship arrives, healthier and stronger, into a system that's already been made survivable. So, would you get on it?
Not as a thought experiment. You, specifically, with your family, knowing all of the above. Not many people would, and the trap is doing exactly what it does. Not by making the voyage impossible, but by making it obviously unwise. So the weight keeps looking wiser the closer you examine it, which is when we have to ask what waiting actually costs. And we've measured that. The answer isn't zero. Here's the mechanism, and it needs building carefully. The universe is expanding, and the expansion is speeding up. Distant galaxies aren't just moving away from us. The rate at which they move away is increasing. Now imagine sending a beam of light out from here, tonight, and letting it travel forever. There are galaxies it will reach, and there are galaxies it will never reach, because the space between us and them is stretching faster than light can cross it. Not because anything is moving faster than light, because the road itself is getting longer while you're on it. Draw a sphere containing everything the beam could ever get to. That's the boundary of everything we could ever touch, influence, visit, or send a message to, even at the maximum speed physics permits. Inside that sphere are roughly 20 billion galaxies. That's an enormous number, and it's also a limit, because we can see a great deal more than that. Less than 5% of the galaxies visible in our telescopes tonight fall inside the sphere we could ever affect. The other 95% we can watch and photograph and study and never touch. And the sphere is shrinking. Every year, its radius drops by about 1 light year. Every year, roughly 3 entire galaxies cross the boundary and are gone from our reach permanently. 3 galaxies a year is thousands of stars every second. Right now, while you're lying there listening to this, stars are leaving. Not dying, leaving. Continuing to burn, perfectly intact, on the wrong side of a line that can never be recrossed. A few thousand of them between the start of this sentence and the end of it. And it's been happening the whole time. Early in cosmic history,
That sphere had a radius of nearly 63 billion light-years. Around 90% of everything that was ever reachable is already lost, and it was lost before anyone existed to want it. Run it forward and it gets starker. In about 150 billion years, our own group of galaxies is cut off completely. Everything outside it becomes unreachable forever. At that point, we'd have 55 galaxies out of 20 billion. So the meter is running, and it's been running since before the Earth formed, and every year of delay is measured in whole galaxies. That looks like the argument that finally breaks the deadlock. It looks like the reason to go now. And then the same analysis does the division, and the answer turns around completely. A year of delay costs about 1 part in 5 billion of everything we could ever reach.
1 part in 5 billion. If you had $5 billion, a year of waiting costs you $1. This is shocking discovery number 6. Which means this. Suppose waiting a single year improves our speed, or our chance of surviving the trip, or the quality of what we build when we get there. By even 1 part in 5 billion, then waiting is the correct decision. The one clock in this universe that genuinely runs out has just told us to take our time. 2 completely different fields have now handed us the same instruction. Technology says wait, cosmology says wait. They were never in conversation with each other. They agree anyway. And here's where this stops being about us. Read the original paper carefully and you notice something. Nothing in the argument is about human beings. There's no assumption about our biology. Nothing about our lifespans, our psychology, our politics, our appetite for risk. The only ingredient is a civilization whose ability to travel gets better over time. That's it. The whole requirement. The author says so himself in plain language. This affects the expansion of all civilizations, not ours, all of them. Any species anywhere that improves at moving things will eventually build something that can leave. And at that moment, someone in that species will point out that the next machine will be faster. And the curve they draw will have the same shape ours does. A steep fall, a bottom, and a long climb. The numbers change, the species changes, the shape doesn't. And buried in that same paper is an aside. He considers a civilization that manages 1% annual growth in travel speed. Just 1% held steady. And he notes that at that rate, the galaxy would be full of travelers. Not eventually, already. So he draws the conclusion. Interstellar travel does not appear to be commonplace. There must be delaying factors. Then he adds this: if a traveler from another star ever did arrive here, that would be very bad news. Not because of what they'd want, because of what their presence would prove. It's the coldest line in the literature, and he leaves it as an aside. It would mean somebody had sustained the growth rate that fills a galaxy. And it would mean a wave was coming behind them, arriving soon, on a schedule we couldn't influence. We've never seen that. We've also never seen anything else, and we have looked properly. It's worth saying so, because the usual assumption runs the other way. The largest search ever mounted is aimed at 1 million nearby stars. It has run for about a decade across 2 major observatories, and it has piled up more than 20 petabytes of radio data. Fill ordinary laptops with that, and you'd need something like 20,000 of them, every one crammed to the last byte. It's the most sensitive survey anyone has ever conducted. Nothing. No narrowband transmitters, no engineering signatures, no repeated structure that isn't ours. And in December 2025, a visitor from another star system passed through our neighborhood. We pointed a 100-meter dish at it for hours, across 4 frequency bands. The search was sensitive enough to catch a transmitter of 100 milliwatts. That's about the power in the little indicator light on a smoke detector at interplanetary distance. Nothing there either. So we have a trap that applies to every species that could ever be in it. And we have a sky that behaves exactly as if every species is in it. Here are the explanations still standing. There are 4. None of them is comfortable. Let's start with the one that lets everybody live. They're not gone. They're asleep, and they did it on purpose. This is the version published in 2017. The mechanism comes from thermodynamics rather than astronomy, which is why it took so long for anyone to think of it. Erasing a bit of information costs energy. That's not an engineering limitation. It's a flaw set by physics. And the flaw scales directly with temperature. Do your computing somewhere cold, and each bit costs less. Do it somewhere warm, and each bit costs more. Now look at where we live. The universe today sits at about 2.7 degrees above absolute zero. That sounds cold, and by kitchen standards, it is. Your freezer is warmer than that by roughly 250 degrees. But cosmically, right now is the warm era. As space expands, that background temperature keeps dropping. It falls, and it eventually reaches a floor. That happens in something like 1.5 trillion years. By then, the universe is about 100 times older than it is tonight. And here is what waiting buys. Take one battery, spend it now, and you get a certain amount of computation. Spend the same battery at the cold floor, and you get a far larger number of computations. Writing it out takes a 1 followed by 30 zeros. So if what you care about is thinking, and you want to think as much as it is possible to think, the strategy is obvious. Gather everything you can reach, then stop, then wait for the cold. That's the argument. A civilization that expanded early, took what it needed, and went quiet. Not dead, just unwilling to waste almost everything it owns. What it explains is exactly what we observe: silence without extinction. Galaxies that look untouched because nobody is currently touching them. What it doesn't explain is the objection published 2 years later, and the objection is serious. The argument assumes you can only dump waste heat into the background of the universe. But the universe today is full of things that are already cold and already far from equilibrium.
There are reservoirs you could pour entropy into right now, without waiting 1 trillion years for the sky to cool. If that's right, the waiting buys far less than claimed, maybe not enough to be worth it. So this one stays open. It's a version, not an answer, and anybody who tells you otherwise is ahead of the evidence. There's another explanation that requires nobody to be patient at all. Suppose some civilizations simply go. They don't run the calculation, or they run it and ignore it. They expand outward at a serious fraction of light speed, visibly rearranging everything they pass through. A model published in 2021 takes that idea and does something clever with it. It fits the parameters to what we don't see. Run it, and we get this. They'd expand at something near half of light speed. At that rate, you'd cross from the Earth to the Moon in about 2.5 seconds. They'd appear rarely, roughly 1 per million galaxies, which is about 1 grain in a large bag of sugar. And they'd already hold somewhere between 40 and 50% of the volume of the universe. The nearest one, on those numbers, we'd meet somewhere between 200 million and 2 billion years from now. The dinosaurs died 66 million years ago, so this is anywhere from 3 times that far into the future to 30 times. Now, why does this sharpen the problem rather than solve it? Because of a separate piece of work from 2013 which asked what a single star system could afford. One system, fully exploited, holds enough material and energy to fire a probe at every galaxy we could ever reach. And the launch phase isn't an epoch. It's measured in hours. Which means expansion isn't a long grind for anyone who decides to do it. It's one project, done once, by one civilization, in one place.
So if any species, anywhere, at any point in 13 billion years ever made that decision, the edge of it should be visible. It would look like a region of sky where the galaxies are wrong. Different spectra, missing light, something. That model does explain one thing. It explains why we're here so early in cosmic history, which is otherwise a real puzzle. It does not explain why the sky looks untouched. And the third possibility is simpler than either and much worse. Nobody is waiting. Nobody went. Growth just stops. We already know what the calculation does when the rate falls. Take the number down to 0.5% a year. The departure date moves out past 2,000 years with a voyage of 4 centuries on top of it. Slow it further and there's no useful journey at any date at all. The bottom of the curve doesn't move. It stops being reachable. And there's a version of this argument that skips technology entirely and looks only at energy. That one is harder to argue with. Energy is not a matter of cleverness. The study asks a simple question. Forget propulsion systems, forget engines. Just count the raw kinetic energy the vehicle needs and assume a generous slice of the world's total energy production gets devoted to it. Then ask when we could afford it. For a minimal colony ship, the earliest date is around the year 2200. For a small probe to Alpha Centauri, around 2500. The year 2200 is about as far ahead of tonight as the American Civil War is behind it. And those are the optimistic ends. The whole thing runs on an assumed growth in world energy production of 1.9% a year, give or take 1.7. Look at that error bar. It's almost as large as the number itself. Take the pessimistic end and the dates don't shift by decades. They shift past the year 4000. So where do we actually sit tonight? Global energy demand grew about 2.2% in 2024, which was faster than the decade before it. In 2025, it grew about 1.7%. We're on the curve. Barely. Within the band, near the middle, no better than the assumption. And the speed record still hasn't moved. So there's the third possibility. Not a galaxy of patient elders, not a galaxy of conquerors, a galaxy of civilizations that each looked at the arithmetic and agreed with it, and then discovered that the growth their plan depended on had quietly leveled off, while they were being sensible. Nobody dies in this version. Everybody just stays home, forever, for good reasons. Which leaves one more possibility, and it's the only one with a door in it. The trap only closes if the goal is to arrive first. That is the whole thing. It's stated most clearly by the engineer who named the incessant obsolescence problem in the first place. Having named it, he went back and dismantled his own idea. Go through the motives one at a time and watch what happens. If your goal is to reach the destination before anybody else, then yes, being overtaken ruins everything, and the trap is total. But if your goal is to leave Earth at the earliest possible moment, being overtaken is irrelevant. Somebody passing you doesn't undo your departure. If your goal is insurance, a second home for the species in case the first one fails, then flight time doesn't matter at all. What matters is that the ship exists and is moving. It could take 10,000 years. The insurance is the same. If your goal is to build the capability itself, then launching sooner and more often is strictly better, because that's how capability gets built. The equation never changes, not one term. The question it answers does. We spent tonight assuming that reaching a star means reaching it first. That assumption was never in the physics. We put it there. And there's a second door, And we've already met it. The 22-year threshold. So you don't have to move the star, you have to move the travel time. Bring any destination close enough in years rather than miles, and the entire structure evaporates. Now let me say plainly where that leaves us, because softening it would be dishonest. The most serious near-term proposal we have is a probe designed for launch around 2036. 860 kilograms, about the weight of a small car. It would swing past Jupiter and leave the solar system at about 7 astronomical units a year, which is roughly twice Voyager 1. 1 astronomical unit is the distance from here to the Sun. After 50 years, that probe would be around 350 of them out. Alpha Centauri is about 268,000 astronomical units away. So in half a century, the best thing we currently know how to build covers about 1/800th of the distance to the nearest star. On that trajectory, the full trip takes something near 38,000 years. 22 years of travel is the threshold. We are not close to it. We are not within a factor of 100 of it. The equation has a door. What it doesn't have is anyone standing at it. Which brings us to the thing nobody has costed, and it isn't the ship. We've spent tonight talking about propulsion, energy budgets, crew genetics, hull erosion. Every one of those is an engineering problem, and engineering problems get solved. Slowly, expensively, but they get solved. The hard part is different. The hard part is holding one intention steady for 9 centuries. Not a wish, not a tradition. A specific technical plan with a launch date, maintained continuously, funded continuously, audited and corrected through everything that happens in 900 years. Do we have any evidence that a species like ours can do that? We have one piece, and it's thinner than you'd want. In the year 578, a carpenter was brought to Japan to build a temple. His family workshop stayed in business afterward, maintaining and rebuilding that temple and others. It ran for 40 generations under the same family without a break. It survived civil wars, it survived famines, it survived a period when the government of the day tried to eradicate the religion the whole business existed to serve. Tens of thousands of temples were destroyed. It survived a world war and the firebombing of Japanese cities. 1,428 years. Then, in 2006, it ran out of money and was absorbed by a larger construction group. It still builds temples. It is no longer its own thing. So there's the record. The longest continuous purpose our species has ever managed is about 1.5 times the weight we'd need. And it ended within the lifetime of most people listening to this. Now put yourself somewhere in the middle of that weight. Not at the start, where the decision gets made. Not at the end, where the ship leaves. Somewhere around the year 2500. You inherit a plan you didn't choose. You can't complete it. You won't see it completed. You can't even verify it. The growth rate it assumes can only be confirmed over centuries, and you only get to live through one slice. You pay for it. Your whole society pays a fraction of its output every year toward a launch none of you will see, using an estimate none of you can test, aimed at a star whose planets may not be where the plan says. And you have to hand it on intact, to people who will feel exactly the same way about a plan that is by then even older. Ask yourself honestly whether you'd keep paying. Then ask whether you'd blame the generation that stopped. That's the state of it. And what's left over isn't an answer. It's a short list of things we don't know, and the list matters more than any conclusion we could reach tonight. Does the growth curve continue at all? Everything tonight assumed it does. The one number that would prove it hasn't moved. If it has stopped, does the departure date move out to millennia, or does it stop existing entirely? Is arriving first even the right goal,
Or did we build a trap out of a preference and then mistake it for physics? And if the silence out there is a decision rather than an absence, is it one we're already making? Quietly, every year, without ever having voted on it? We don't know. That's not a rhetorical flourish. Nobody knows. So here's what we've established. The distance was never the problem. The ship was never the problem. The problem is that every year we get better, and every year that gives us a reason to stay. The problem is that leaving early wastes the voyage, and leaving late wastes the wait.
The problem is that the correct departure date sits centuries beyond every generation that ever calculates it. Anyone who goes knowing they'll probably arrive second. And anyone who waits may be waiting for growth that already stopped. And yet, look at what we're doing here. A species that has never sent a person past its own moon has worked this out. With arithmetic, a teenager could follow. The optimal century for a journey it cannot make, to a star it will never see, in a future none of us will occupy. Rock falls. Rock falls the same way twice. Something notices that it does. Something writes down why. Something uses that rule to compute a date 900 years out, and understands that the date is not for them. That's not nothing. That's a kind of reach that has nothing to do with speed. But let's be straight about what it doesn't do. It doesn't move the record. It doesn't shorten the wait by a single year. It doesn't stop the galaxies leaving. They're leaving right now, thousands of stars at a time, and none of us can do anything about it. Understanding the trap is not the same as escaping it. We may understand this perfectly and never leave. Thank you for joining me on this journey through 900 years of arithmetic and the strange, patient silence it might explain. It's not a comfortable place to spend an evening, and I'm glad you spent it here. If you'd like more of this, subscribing and leaving a like genuinely helps this channel keep making it. And in November, a spacecraft launched before most of us were born will quietly cross one light day from Earth, still moving, still first, still unpassed after 49 years. Good night, and may the things you're waiting for be worth the years you give them.